Hi, in this video, I will demonstrate how you can use an analog touch sensor module interface to ESP32 using MicroPython programming language. What I have here is the analog touch sensor module from Gorilla Cell ESP32 development kit. This module is capable of providing 4 unique touch input on a single pin. In other words, each touch sensor corresponds to a different analog values. We can read the analog value of the pin using the built-in ADC peripheral of the ESP32. Also, please be noted that MicroPython implements ADC on GPIO32 to GPIO39 only. The analog touch sensor module has 3 pins, which are G for the ground pin, V for the supply voltage, and S for the analog input signal pin. In order to follow this lesson, you will need an ESP32 development board, a Gorilla Cell ESP32 shield, a 3-pin DuPont jumper wires, and of course, the analog touch sensor module itself. Now let's assemble our demo circuit by attaching the DuPont jumper wires to the analog touch sensor module, and attach the other end of the DuPont jumper wires to the ESP32 shield. Make sure that the connection of the DuPont wires to the sensor is such that black is to the ground, red is to the VCC, and yellow is to the signal pin. While in the other end, match the colors of the wires to the shield's pin headers, such that black is to black, red is to red, and yellow is to yellow pin headers. For this lesson, I choose GPIO32 to serve as the input signal pin from the analog touch sensor module. Now let's power the ESP32 shield through a Type-C USB cable. And make sure that the power switch is set to on state. Now let's connect the ESP32 to the computer through a micro USB cable. Now for the software part, I prepared here 3 example source code for this demonstration. For example number 1, we will read the analog value of GPIO32, which is the pin connected to the analog touch sensor module, and convert it to its digital representation using the built-in ADC peripheral of the ESP32. Clicking the Run button returns 0 because no one is currently touching the analog touch sensor, which is printed by this line of code. Let me copy it and paste it in the REPL. Let me touch number 1 and hit enter, which returns an ADC value of 668. Let me open a notepad to record the equivalent ADC value of each touch sensor. Touch sensor 1 is equal to 668. Let's read again the ADC value. Press touch sensor number 2 and hit enter, which returns 1513. And let's record it in the notepad. Now let's read the ADC value of the touch sensor number 3, which returns a value of 2333. And finally, let's get the ADC value of touch sensor number 4, which returns a value of 3199. These are the equivalent digital representation of each analog touch sensor. Analog values tends to change from time to time, and we need to catch each touch sensor touch event. To do that, we need to check for a lower and upper limit values. For this lesson, I will use ±30. Now let's briefly discuss example number 1. It begins by importing the pin class from the machine module in order to access the ESP32 pins. Then import the ADC class from the machine module in order to use the built-in ADC peripheral of the ESP32. Here, we created the ADC object for the analog touch sensor module. by creating the pin object named P32, which is connected on GPIO 32, with the pin direction set as an input. Then creating the ADC object named ATS, short for Analog Touch Sensor, using the P32 pin object. Then configure the ADC peripheral with an attenuation of 11 dB in order to read a voltage range of 0 volts to 3.3 volts. And finally, print the ADC value to the REPL. Now let's go to example number 2. This example uses the same imports and object instantiation. Here, we use a while loop to catch touch event on the analog touch sensor by reading the analog touch sensor value and save it to the ADC value variable. Here, we will use the recorded ADC values from example number 1 and replace the limit range in the if statements, which catches the touch event on each analog touch sensor key input. Let's save our modification and click the Run button to execute example number 2. Notice that currently nothing is printed in the REPL, but when I press touch sensor number 1, it returns you press number 1, or press touch sensor number 2, which returns you press number 2, or press touch sensor number 3, or the touch sensor number 4. Lastly, let's have a simple application demonstrated on example number 3. For this, we will use an 8x8 dot matrix display. Our objective is to control the movement of the turned-on single pixel on the dot matrix display using the analog touch sensor module. First, connect a 5-pin 2-point jumper wires such that black is to the ground, red is to the VCC, yellow is to the data input pin, white is to the clock pin, and blue is to the chip select pin. Now attach the other end of the 2-point jumper wires to the dedicated SPI port on the ESP32 shield. We will use a MOSI pin with GPIO 23, S-clock pin with GPIO 19, and chip select pin with GPIO 18. Also import the MAX7219 from MAX7219 driver library for handling the dot matrix display. Now instantiate the dot matrix display object named DOT or dot with 8 columns, 8 rows, and using the instantiated SPI object. I also set the dot matrix to display maximum brightness, which is a value of 15. Then declare a global variable for storing the current position of the turned-on pixel, which is in column and row position. In the main loop, we read the ADC value and save it to the analog value variable, which is used for identifying the specific touch sensor input. And with respect to the touch input, the column and row position can be incremented or decremented accordingly. To update the dot matrix display, first clear the display, then set the column and row position of the pixel to be turned on, and lastly, update the display using the show method. You can provide some delays between iteration, such as 100 milliseconds. Now let me click the Run button to execute example number 3. Now we can control the movement of the turned-on pixel on the dot matrix display. Number 1 and number 2 controls the horizontal movement, while number 3 and number 4 controls the vertical movement. So that's it. I hope you enjoyed this video. As always, the source code that is in here, including other information, can be found in the companion blog post for this video at tech.to.tinker.blogspot.com. Links in the video description. If you have any concern regarding this lesson, please write your message in the comment section. Please give this video a thumbs up and share this to your friends so that it can reach more people who might benefit from this. Please don't forget to subscribe so you will not miss video contents uploaded in the near future. Thank you and have a good days ahead. See you next time. God bless.